Alright, part 3. When you're comparing two proportions, or they call that difference, you have to do slight variations or slight modifications essentially. So first off, the standard deviation is the Pythagorean theorem when you're doing two of them comparatively basically. Um, so the standard error looks very similar except you just have to do two of them added together. And then, so this is your standard error, and if you add in the critical value, becomes the margin of error, right? So the whole thing is the, margin of error. And of course, the difference of the two proportions. So you're basically seeing what is the difference between the two proportions, basically. All right, that's what the comparing two proportions problems are basically about. So let's go down to here. All right, so male teenage drivers who wear seatbelts when sitting next to a male passenger and the proportion who wear seatbelts sitting next to a female passenger. So basically, if you're a boy, are you making some kind of difference in your decision making sitting next to a boy or a girl essentially? Alright, so let's copy this down to here and change out our values. Okay, so what do we have here? So 1277, let me think about the math here. Let me scroll down. Okay, so 1277 out of 1433, so I did a little bit of math here, this might be wrong, but we'll figure it out. So 12777, so if I add 1431, that gives me 4208. Okay, and then this one, the second population, 1363, and I add 1400 to it, so that would be 2763. Alright, which way gives me positive? So if I kind of do a little bit of math real quick. Alright, so 277 divided by 4208 and 1363 divided by 2763. Okay, so if I do it that way, it's going to be a positive answer. The other way would give me a negative answer, so that's fine. Okay, so we want to take those now and put them up here. Times. And put those here. Copy. Times. Okay, so that'd be the 1431. 31. Yes, right? So success and failure for the first one, and success and failure for the second one. So 4208. 2763. Alright, so we're going to copy all that to here. So this is not really P1 and P2. There's no population 2 in real life. So, the female passenger, so this is female. And this is male, I believe. I'm reading this right. If the study found that among male teenagers with a male passenger, right, so this is female minus male. The difference between female minus male, right? Because this one's the female passenger, this one's the male passenger. Okay, so we also need the z value, the critical value, because again, for proportions, we're only going to do z. There are t ones, but those are specialty cases. We don't need to do those. So normal dot inverse. Okay, so basically, if a problem doesn't tell you what the alpha is or what the confidence level is, you're going to assume alpha 5% or a confidence level of 95%. So again, if the problem doesn't give you an alpha or it doesn't give you a confidence level, okay, if you're not instructed to calculate one based on sample size, you're going to use what's called the Fisher rule. The Fisher rule is basically 95% confidence or 5% alpha basically. So if I do 95% confidence, it means I'm 5% not confident, okay? So basically the Fisher rule, right? So alpha is 95%, or alpha is 5%. Okay, so they use that by default. It's a statistician called Fisher, which believed 1 out of 20 was the best way to do things. So the stats books tend to use it as a default if nothing is specified, basically. Okay, so 95% is the default confidence interval. So 5% is not confident, so half that's 2.5. So if I add 2.5 to 95, I get 0.975. Okay, so that is my z value. All right, now I can put this into my spreadsheet. So the things I need in my spreadsheet, let's add another, rename this. We're going to go part 3. Part 3. Okay, so we want, let's make this bigger, it's too small. P female hat, P male hat, right? Okay, so remember correctly, that was 277 divided by 4208. And this is 1363 divided by 2763. Okay, so my z value is normal dot inverse 0.975 comma 0 comma 1, right? So basically I'm inverting the area or the probability back to a z value, and 0 and 1 are the default values for mean and standard deviation. Okay, so basically the Q for female and the Q for male, right, is basically 1 minus each of these, right, equals 1 minus each of these, right? So success and failure. So I believe this is wearing your seatbelt, not wearing your seatbelt, wearing your seatbelt, not wearing your seatbelt, right? Notice these add up to 100%, correct? All right, so if I'm going to cheat a little bit here. And I'm going to take, oops, where is it? I'm going to take this, copy it to my spreadsheet, just so we can see it. Right? Okay. All right, so first is P female minus P male, that's the first part, minus the z value times the square root. Okay, and we have two different fractions if you kind of look at this, right? You have the left fraction and the right fraction. So the left fraction is P times Q. Oh, I didn't do an n, but oh well. We'll just type it in manually, I guess. There's the first fraction plus the second fraction, P times Q divided by 2763. I probably should have made a box for the n values, but oh well, we can change that in a minute. Let's do that. So close paren for the square root. So I have parentheses for the square root, parentheses for each one of the fractions essentially. So we can do the numbers for female and the numbers for male. Oh, I screwed up here somewhere. We'll fix that in a minute. All right, so 4208 and 2763. Okay, those are the numbers. Okay, what seems to be the issue here? Oh, I didn't put the divide symbol there for some reason. All right, we can get rid of this and put this number here and that number there. Okay, that's our good references now. All right, so that matches this down there. What did we do wrong? Interesting. Oh, I didn't delete that. That's why. Okay. I think I hit the, what I did was I hit the parenthesis and not the divide button, right? Because it's the success and failure divided by the quantity. Success and failure divided by the quantity. I just hit the wrong button is all. Okay, there we go. All right, so I'm going to copy all of that formula. Copy. And paste it there. But I'm going to change this to a plus, right? Because, oh, did I screw this up in my notes? Oh, I did. Look at that. That's a plus, isn't it? I think I copied pasted in my notes. Oh, no, it's right there. That's a plus. I don't know why it became a minus. Oh, you know why? Because I copied from there to there. That's why. So I had it right, but when I copied, I didn't change it. Okay, so let's go back to our spreadsheet here. So basically, between 13% and 17%-ish, right? Hopefully. 277. Just double checking my values here. I think we're good. Okay, we'll just go with it. Okay, so let's write those values down. 1319. So we'll say 0.1319 is less than P. You know, I'm going to copy these actually. I thought there'd be slightly different values, but I might be wrong. 17091, I guess. I'm at 1791, 1319. That's good enough. I'll put 3 dots. Okay. So basically, that is the difference between the two, right? So let's write something in context now. So we are 95%, right? Because if we, I don't need R twice, because it's the Fisher rule, 95 by default. We are 95% confident that the proportion of teenage male drivers who wear seat belts when driving next to a female passenger is between 13.19% and 19.1%, no, 17.91% higher than the proportion the proportion of male drivers who wear seatbelts when driving next to a female, then higher than a portion who wear seatbelts when driving next to a teenage male passenger. I like that. And if you had swapped these two, right? If you had swapped these and done 277 and then basically if you swap these two fractions, that would change this answer. You would get a negative answer, which means you would have to flip this right here, because then you would be saying the teenage male drivers with a male passenger is lower than the female passenger by those percentages you would find, which would be in the negatives basically. It will be the flipped answer, which would still technically be right, but to keep in context, I like to give the positive answer, but it's not always necessary. Okay, so you can see the confidence interval is not all that much different for a difference between two than it is one. You're just basically doubling the amount of work essentially. All right, let's do the hypothesis test. So the problem with a hypothesis test is you have to pool or combine the values for the standard error. Okay, so it's not the standard error we just did a second ago for the confidence interval, because the default value for the hypothesis test is that the two populations are equal. If the two populations are equal, you have to combine both samples together, essentially. What's called pooling or combining. So what you'll notice in this book, you'll see a sub-zero, which means the populations are the same, which means combined or pooled. So when you Google it, there's no real agreement as to which one's the proper terminology. I like P sub C myself because I don't like to see P sub P. P sub P is kind of confusing, but P sub C makes sense to me combined, you know what I'm saying? Or you're combining the two populations together. But this book uses P sub 0, which means the populations, the difference between the populations is 0 essentially. Okay. So let's say, for example, we want to know whether the snoring rates differ for those over 30. We found 48 and 136 did not. In older people, we found 318 of 493 did. Or 48 snored, 136 did not. 318 snored, and 493 did not snore, basically. Okay. So, step 1. I don't know why it's doing bold by default. Let's get rid of that. Make this bold. So, yeah, it's double lining. Let's get rid of that. All right, so the parameter of interest, which is still P for these, because it's still proportions from this unit, is the proportion of the population that snores. Sometimes they specify like U.S. citizens or males or females or children, or I'm saying you'd have to be more specific in those cases. All right, so this will be a 2-sample z-test for the proportion of the population that snores. Okay, so the hypotheses here will be a little bit different because it's not a number now. So H sub 0 is our null hypothesis. H sub A. Okay, so we have the proportion of old equal to the proportion of young, right? So you always assume that the populations are equal, or basically think of it this way. Thus, let's do it this. I'm going to copy this. Copy space minus that is equal to 0, right? So basically, we assume that they're the same. Okay. So we're not saying that one of them is more than the other in this question, right? We just think maybe it's different. So it could be a less than or greater than, but this one we're just going to say not equal to. Basically, if I copy this, it would not be equal to 0, right? So this is a two-tailed test essentially. Okay? Because again, these ones can be less than, greater than, or not equal to, just like the single proportion ones, right? The only difference here, instead of using a number, we're comparing two populations. Okay, so again, all three types are possible here also. All right. Okay, so step 2. Step 2. Okay, so n sub young times p sub young. In this sample, we got 48. So therefore, we're fine, right? And I'm going to copy this, old. Oh no, that'd be young, I'm sorry. I don't know why I did that. We got 136. And then I'll copy these. Copy. Paste. And now it's old. 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 Copy those. Copy those. So we got in our sample 318 successes. And what did it say? It says 493. 493. Okay. Let's double check. 130. Yes. Okay. So basically our successes and failures are all more than 10. So we can do this basically, right? And also a couple things. The number of people is less than 10% of the population. Thus, the samples are independent. So basically, if you take somebody from the population, it would make it dependent. But since it's such a large population, taking somebody from the population still makes them independent. The samples are likely random. There's no reason to believe they're not randomly selected, right? So they basically have to meet all these criteria. One, they all have to be more than 10. They have to be independent when selected, and the samples have to be random, right? You can't. And the two groups are independent from each other. You cannot be both in both age groups, right? You can't be in both age groups, and you can't affect the other person. So if I'm old and you're young, I have no, my snoring has nothing to do with your snoring, basically, right? So basically, in these two sample ones, the same as the one samples. One, they have to have the minimum number of samples. They have to be independent and random. But you also have to do the next step, which makes sure they are independent from each other. Okay? Okay, so basically, the mean of the sample set p hat sub old. Oh, that's not what I want. Minus, I'm going to copy that. Copy, paste, young. I think it's old minus young. I got to pay attention. I might have that backwards, but it doesn't really matter. What did I do? Yeah, it doesn't matter. Either way, it's going to be 0, right? And then I'm going to copy this, change that to standard deviation or standard error. Okay. All right, so, which is also known as standard error combined, right? All right, so I'm going to do this, and we need two fractions. We need a fraction plus a fraction. Okay, so the first one is out of 184. The second one was out of 811. Whoops. And then these are two fractions. This was... Now we got to do a little bit of math. Oof. Let me think here. I got to scroll up, do a little math in my head here. Okay, so... My successes are 48 and 318, which gives me 366, right? For a grand total of 318 plus 493 is 995. So the total number of samples is 995. Okay, if I add all these together, and the successes are 48 plus 318. Okay, and then failures. Let's see, it'd be 493, 196, that'd be 629 and 995. Okay. And I can take this, copy, paste. Oh, I see a typo. That's supposed to be Q, right? Success and failure. Make sure I got those correct. Yes, did not snore as 493, did not snore as 136. Okay. So basically I added them all together and I got 995, right? So add all those together, you get 995. So the 48 and the 318 added together are 366, and the 136 and the 493 together are 629, right? So if we look at the formula, the standard error in this case is the pooled amount, basically. Okay? Um, so I have to add them together, combined amount, basically. All right, so I think I have it so far. So let's go to step 3. Step thrice. Actually, do I want to do that? I'm going to delete that. I'm going to cheat a little bit and then go up to here and copy that formula. Okay, get rid of that. All right, equals. All right, so if I kind of think about the fractions here, so my first n1 would be what, 48? Oh, I gotta times. Oh no, that's not 48. That's 48. As we're looking at just the young ones here, right? Or is this the old ones? Might be the old ones actually. I think I got this backwards. So the successes on the old were 318, right? No, I'm sorry, 318 out of the, let's see, 318 plus 493, right? So 318 plus 493 is 811. So 811, 811. Okay. Plus, what was the other one? So the young was 48 plus 136. So that's 184 times. Okay. So successes here are 48 out of 184. Right? So 811 plus 184. So that equals, so the 811 and the 811 cancel. The 184 and 184 cancel. So what does that leave me with? That leaves me with what we got before, which was 366 over 995. Right? So that is the pooled or combined formula for proportion, basically, if you think about it. Okay? All right. Then we get the z value. So I'm going to go up here and where did I put it? Right here. So I'm going to copy that. So observed minus expected. So over the SE. So I believe I did this one old. Was the old one was a bigger one? I forget. Yes, it's old minus young. Okay, I'm old minus young. And then old minus young. There we go. Okay, so we do this ratio here. That is the 318 over 811 minus the 48 over 184 minus 0. Right, I want to keep that just the way that is, right? So What about standard error? Come on, we already have that up here, right? We're just going to take that up here. So we need to put those into the spreadsheet to get the area now. So that is going to give us the area. So math type area equals, and we'll pause there and come back. All right, so we're going to go to our spreadsheet now and put these various things in. Okay, so we want P combined and C combined. So we're going to go to part 3, we'll scroll down, P combined, Q combined, right? So those things are 366 divided by 629. No, 995. And this one is 629 out of 995. Okay. And for young and for old was 184 and 811. Okay, so we have those things there. So we also need the probability of young and the probability for old, right? So the young were 318 out of 811, and the probability of old was 48 out of 184 for snoring. Probability. So that's a basically a guess. All right. So we also, I think we're good. We have everything there. All right. So I'm gonna go back and copy now. So we need to copy this thing right here. Kind of do a little bit of cheating here. That's what we want to get right there, right? Standard error. So we'll put standard error right there. Standard error equals, actually I'll just move that over so you can kind of see it. Move that over to the right. Okay, equals square root. Okay, so we notice we have two fractions here. So the first fraction is, doesn't really matter which one we do. Success and failure of the combined divided by the 184. Ooh, I did that again. I think my divide button is the problem, because I just noticed I did that again from the last time. Okay, so success and failure divided by the 811, and then close off the square root. There's my standard error. Okay, what do we do here? Divide, plus. We did equals. What's the issue? Oh, I did it again, yes. Don't know why I did that. Okay, there we go. There's my standard error. Okay, so that matches that. Now we can go back to our notes here. And we can get the z value. We need to do that, correct? Okay, and we're going to do z, and maybe we'll shove that to the right, maybe. All right, so equals parentheses. So p. So this is the. I forget which one's which here. 318. Look back at the problem. So 318 is the old, so we need old minus young. Okay. So we need old minus young divided by the standard error, right? Combined. So we have negative 0.33. So I think we're good there. Okay. Let's do this both ways, actually. So let's think about it this way. So the last thing we need now is the area. Okay. So if I draw a little picture here, this is a negative z value that we just found, correct? So we want to know this area right here. But this is a two-tailed test, because remember correctly, this is a not equals hypothesis test, which means it's a two-tailed test. We need to actually double the value. Okay, so equals 2 times normal dot distribution. Okay, we'll put the z value in there, comma 0, comma 1, comma true, right? And we get that area there, right? Let's say we did it the other way. We did young minus old versus old minus young, right? So let's switch it. So we'll do z equals, right? We'll do another z here, and we'll switch it, move this over, and we'll do young minus old, okay, divided by the standard error. We would get the positive z value. Oh man, well, whether you do young minus old or old minus young depends whichever way you want to do it. Doesn't really matter. That would be a positive z value over here, which means this area. The problem is when you calculate it, it goes left to right. So that means I have to do 1 minus to get this area over here, because the formula itself is going to give me this area, which I don't want. But then I still have to double it, because it's still a two-tailed test. So if I did that, the area would equal 2 times, parentheses, 1 minus normal dot distribution, right? The z value, comma 0, comma 1, comma true, and then close off the parentheses, right? Since it's the positive z value, it's on the other end, so I have to do 1 minus to get there. And notice we got the same area, or i.e. the same p-value. So which way did I do it here when I typed it? It looks like I did old minus young, which, if I remember correctly, is which one here? 18, old minus young. So that is the negative z value, essentially. Okay, so we're going to say in our thing here that we got a approximately negative 3.33, whatever it was, you know what I'm saying? So that means the, oh, actually, no, let's put the area down here. That means the area is 2 times the normal dot distribution, okay, parentheses, the z, comma 0, comma 1, comma true, and we got approximately 0. I think it was 2 zeros and an 8. Let me just double check. 3 zeros and 8, 5, 9. 3 zeros and an 8. 5, 9, dot, dot, dot. Let's put a little asterisk over here. If positive z. Oh, negative z, negative z. Okay, we're going to copy this, copy, paste, and then put a parenthesis around this. Let's put a parenthesis around this. And do 1 minus. That's if it was a positive z. Right? Because then you have to flip it to the other side of the normal curve, essentially. Okay, so those are my p-values, essentially, right? Okay, so let's do step 4, the last step. Step 4. So essentially, the p-value, well, did it specify in the problem? It did not. So we don't know what this is. So essentially, we're going to assume it's a 95%. It's using the Fisher rule, right? So as a result, the p-value is clearly less than alpha, which is 0.05. Because the Fisher rule assumes a 95% confidence and 0.05 alpha, essentially. Okay, so since it's less than that, we are going to reject the null hypothesis because it's a very small area, which means it made it all the way to the critical region essentially. So it's always basically looking at whether it's less than or greater than alpha. That's really the decision basically. So this means our sample was, our sample proportion is significant and not likely to occur. So it's a very unusual sample, which means the traditional wisdom that the old people and young people are the same was disproven by our samples that we found. So they're not the same. As to whether somebody scores more or less based on age, we don't know. We just know they're different, right? So there is enough evidence, so our sample is enough the evidence, to reject the null hypothesis. So it is likely true that there is a difference in snoring between snoring rates between age groups. Because the default was we don't believe there is, so otherwise there is essentially is the default basically. Okay, so at the end of the day, no matter whether you're going to go one proportion or two proportion difference, what it comes down to is the p-value in the picture essentially. So if we go all the way back, right, is the p-value less than alpha or is the p-value greater than alpha? You might get an equal to case, but that's basically near impossible. So typically people don't talk about that, and it comes back to the picture. Do you need to draw the picture? No, you don't need to draw the picture essentially. So if you drew the picture here, essentially you would have this. So you would have 0.95 for the Fisher rule. So alpha is 5%. So essentially this is 0.025. And this is 0.025. Okay? So we got a negative z-value or a positive z-value. So the question is that if it's a negative one, is it over here or is it over here? Well, our area is less than this, so it means it's in this one over here, right? So this is our z right here, my negative z. So this area is right here, which means it's less than the 0.025 from the Fisher rule, basically, which means it's in the critical region. This is the critical region, essentially. It's in there, which means we found enough evidence. If it was greater, it would have been over here, which it wasn't, because this is all the very conventional samples you could possibly get if you took samples, which we did. But our sample didn't fall in here, it fell over here, which means it was significant enough. We found enough evidence to conclude that the null hypothesis, right, this is the null region. Okay, all right, that's all for part 3.